Today we'll be introducing Big Idea 5, very broad in nature, and we are going to use laws of thermodynamics to talk about the roles that energy play in chemical as well as physical reactions, and we'll be able to explain and predict changes in matter based on their directionality. Very, very broad Big Idea. We'll be getting more into thermochemical calculations as well as an understanding of heat release versus heat absorption. We'll link that to entropy, a measure of disorder in a system, as well as free energy. Some of you may remember it as delta G. So if you had an honors chapter last year on thermochemistry, you're going to see a lot of review in this particular chapter. If you didn't, it really is not that difficult, so I don't think you'll have any trouble with it. So this week and next, we'll be talking about thermochemistry as well as thermodynamics. We're going to start off today with thermochemistry. And there are a lot of definitions here. We're going to go through these relatively quickly. You've seen a lot of it from middle school science, and the definitions are not going to make or break. There are a couple of Bozeman videos that I do recommend that you watch for tomorrow. I think that will help with a lot of the concepts, so we really can focus on some of the calculations you may be asked to do. We've seen thermochemistry asked quite a bit on part 2, so I would think you'll have more of the same this year. Thermochemistry, we're going to see, is the study of the energy changes that occur during chemical reactions. Before we get into that, we want to just review that energy is the capacity to do work or generate heat. Potential energy, you know, is the energy associated with the object's position, versus when you've got movement, you're talking more about kinetic energy. We've seen kinetic energy in action with some of the molecules both vibrating and rotating that we talked about earlier in the year. Work is the product of force times the distance the object or whatever it is traveled. We'll talk very briefly about work in this chapter, nothing that I think will affect you throughout. When you think about thermochemistry, you essentially want to divide the universe into 2 parts, a system and the surroundings, and we're going to talk about heat lost by one and gained by the other. So if the system loses heat, the surroundings gain it. If the system gains heat, then the surroundings lose it. And again, there's a Bozeman video on system and surroundings, and I highly recommend that you take a look at that tonight for homework. The part of the universe that we're studying is referred to as the system. Typically, that's the chemical reaction, sometimes the reaction vessel that chemical reaction is occurring in, such as a test tube, Erlenmeyer flask, beaker, etc. In an open system, you're going to see interaction with the surroundings. So if you have a pot of boiling water, or you have a beaker full of solution or 2 solutions that you've reacted together, you've got an open system as opposed to a closed system in which you still can get energy exchange, but you're not going to get matter exchange with the surroundings. So you're going to cap it in some way, maybe put a rubber stopper in it, etc. In an isolated system, that might be nice today because it's a little cooler out. So if you wanted a thermos of hot soup for lunch, a thermos is an isolated system in which neither energy nor matter is exchanged. The surroundings is everything outside the system, and you'll see that it's going to really focus on the parts that interact with the system. And again, that Bozeman video would be very helpful. If it's not clear to you which one it is, I can point it out at the end. The total energy contained within a system is referred to as internal energy, abbreviated either U or E. In your textbook, it's abbreviated with an E. In some of the other books, it's a U. Kinetic versus potential, we've talked about that already. So kinetic or thermal, you'll be dealing with translational, rotational, vibration, movement. We've talked about that before. Potential or chemical, these are the interaction between particles of matter, such as your intra and intermolecular forces that we've talked quite a bit about in the first semester. Another term you want to be familiar with is heat, as well as its abbreviation Q. This is the energy transfer between a system and its surroundings, and it's caused by the difference in temperature. For example, if you went skiing over break, after you went skiing, you probably were very cold, although I sincerely hope you didn't go out west where it's like 10 to 40 below. I don't think I could handle that, and I grew up north. But heat transfers from the hot object to the cold object. So if you did go skiing, when you came back in, maybe you took your socks off and put them by the fireplace, heat transfers from the warm fireplace to your cold toes. Or if you had a mug of hot chocolate, the heat would transfer from the mug of hot chocolate to your cold hands. Work, energy transfer between a system and its surroundings. A system does not contain work, but you'll see that energy can be transferred from one to the other. Now with heat, you're talking about it being due to the temperature difference, so that's the key distinction between the two. We're not going to deal with pressure volume work, so we'll just skip that right now, and we're going to link heat with work through internal energy. So internal energy, state functions, and the first law of thermodynamics. Now internal energy, as we said, is the total energy contained within a system. This is a state function, so that means it only depends on the beginning point and the end point, the final and the initial, and you can subtract the two to get the change in internal energy. And that will be important. If something is a state function, you can calculate its quantity simply by subtracting the initial from the final. Now, neither heat nor work is a state function because they depend on the path chosen. When you have a state function, it doesn't matter what pathway you take. When the bell rings today, you're in 4th hour, you're going to 5th. Doesn't matter if you go to your locker, go to the bathroom, go hang out with your friends, or whatever it is you do during class changes. We only care that you were here, and then you're going to be at 4th hour. So you can subtract the two to get the change, if you will. With heat and work, they're not state functions, so you can't calculate them in that regard. But when a property is a state function, you can subtract the initial from the final to get the change in internal energy. The law of conservation of energy: for a physical or chemical change, energy is neither created nor destroyed, but rather just exchanged between a system and its surroundings. If the system loses, the surroundings gain. If the surrounding loses, the system gains. And you can think about that in a very simplistic diagram, but as I said, the Bozeman videos will be extremely beneficial to you. So for example, if this box represents the universe, this can be the system, this would be the surroundings, and the sum of the two represents the universe. And again, if the system loses heat, the surroundings gain heat. If the system gains heat, the surroundings lose heat. And again, the video will go into that in quite some detail, and I think it would be helpful to you.
Would you call that like endo-exothermic?
Absolutely, and that's exactly the direction we're going. So what you're going to see here is that the system loses heat, you've got an exothermic reaction, the system gains heat, and you have an endothermic reaction. And that's exactly the direction we're going. Good. The first law of thermodynamics says that the sum of heat and work is equal to the change in the internal energy. And what you'll see here is that when energy is entering a system, the change in internal energy is positive. When heat is absorbed by the system, Q will be positive, and that would be endothermic. If work is done on a system, positive value for W. So if you went over break to get a massage, a lot of work was being done on your back or your muscles, and hopefully you walked out of there with a happy face because you would have felt good as work was done on you. Happy or positive right there. Oops, my thingy's dying. For work. When energy is leaving a system, it's going to have a negative value. For example, heat given off by a system, Q will be negative. That would be exo or endothermic? Exo. And work is done by a system. When you walk out of here at the end of the day, being first day back, you're going to be pooped. You're not going to have anything less than in the tank, or essentially a negative reserve. So W here would be negative. Simple example shown here. If you saw this, it would be, I would think, in a multiple choice format. In a process in which 89 joules of work is done on a system, 567 joules of heat is given off. What is delta U of the system? So if work is done on a system, that's like getting your massage, positive value for W. Heat's given off, so this would be endo or exo. Exo, the delta U of the system is the sum of those two values, and in this case, you're going to see negative internal energy, and so energy is leaving the system, picked up by the surroundings. Questions? Pretty straightforward so far? There are some very simple examples and problems in your textbook at the end of your chapter in chapter 6, and I would recommend that you spend some time tonight doing some of these very easy problems just to make sure you have the concept so it's not a mad rush the night before the quiz. Endothermic reactions versus exothermic reactions. I think I flew down a little too far, and this is exactly where we were going. You already picked up on it. In an exothermic reaction, we know that heat is lost by the system but gained by the surroundings. And this is a very tricky point in regard to temperature increase. And sometimes it's the way it is given. So be careful here. We'll make the distinction clear. In an exothermic reaction, the chemical energy in the system is going to be converted to thermal energy. In an isolated system, you're going to see a temperature increase in the system. And this is a little confusing because you're thinking, oh, heat is given off, you should see a decrease in temperature. Be very careful here and always think about it in regard to what perhaps you feel when you touch that flask or reaction vessel. So what you're looking at here, for example, when you dilute acid in water, we already stated earlier this year that it's very important to have a bed of water that you will then put the concentrated acid in to dilute it, because the reaction is so exothermic. This way some of the heat can be absorbed by the water rather than the reaction vessel just exploding. So if you put your hands around the outside of that container, you'll feel the heat release, and essentially it's what you feel that determines that temperature increase or decrease. If your hands around that vessel feel warmer, then the temperature increased in terms of this exothermic reaction. And this is a backward concept, and what you might see in regard to a question being asked is it will say a reaction is carried out in which an increase in temperature is recorded. Is the reaction endo or exothermic? And if you record an increase in temperature such that the final is greater than the initial, that's exothermic. Be careful there. It's a very confusing concept. when you want to clear your drain pipes, you may pour Drano down them and then you flood it with water. Drano is essentially lye or sodium hydroxide, a strong base. That reaction is highly exothermic. Heat is released. That heat will melt the grease that's in the drain pipe. Now, if the drain pipe's all clogged up with like kinky, yucky hair like mine, then it's not going to help. You have to get the hair out. But we're just talking about melting things that are in there that can be melted. In an endothermic reaction, the thermal heat now is going to be converted to chemical, or thermal energy converted to chemical energy. Now what you're going to measure is a decrease in temperature in the system, regardless of the type of system you have. You're going to measure a small temperature decrease. So the initial temperature will be higher than the final, and this is what you're going to be doing in the lab next week when you first determine which substance would be the best to make a hand warmer in terms of heat release as well as safety to yourself and the environment. On the flip side, for those of you who watched football yesterday, it appeared to there were not only quite a few injuries, but also at least 2 concussions, I would say, and they were constantly using those cold packs on the sideline. And what you find with these instant cold packs is that you've got 2 compartments. You smack the cold pack, allowing the 2 sections to mix. You've got ammonium nitrate in one and water in another. And when the 2 mix, the reaction gets colder and colder, and then you can place that on your knee or whatever it is that you have injured. And this is an endothermic reaction with the decrease in temperature. For the hand warmers that we're going to generate, we clearly want an exothermic reaction, but you'll see examples of both when we run through the different substances next time.
I'm just confused about the isolated system and how, like, because it says isolated system temperature increase in the system and then decrease, but it seems like it's backwards.
It's a very backward concept, because you would think that if heat is being released, you would measure a decrease, but it's not what you measure. And when you do the lab, you'll see it, because you'll feel it. Think about what you feel. And I always go back to the dilution of acid example, because I know whenever I dilute acid, it gets hot, I can feel it, and I also see the smoke coming out of it. And I know that's exothermic, and the fact that it's smoking reminds me that that's an increase in temperature. But it is a backward concept, and the way you'll see it is they'll either tell you it increases or decreases, and you have to match it to endo or exo, or they could be sneakier with it and give you an initial and a final temperature and just look at whether it's climbing or going down.
So it's just backwards in the isolated one? Or
No, in all of it. It's all of it. You see, if you look at exo right here, see it says temperature increase?
Yeah.
Okay? In a non-isolated system, you can actually, in some instances, visualize the heat given off because you'll see smoke.
Mm-hmm.
But regardless, you're going to have a temperature increase in every single situation for exothermic. And I think the easiest trick to remember it is decrease in temperature, endo, look for the D. And I think it'll be easier for you.
Okay.
All right?
Yeah.
They don't really assess that much in regard to pressure volume. I don't even want to say that much. I haven't seen them assess with pressure volume work at all lately, so I'm not really going to hit this section. I do want to mention that heat of reaction is typically Q of reaction. Heat is Q. Reaction abbreviation is RXN. We're going to look at how much heat is exchanged between the system and the surrounding, and you're going to hold it at constant temperature. But what we really want to focus on is enthalpy. Enthalpy is something that they do assess quite a bit. Enthalpy is abbreviated with an H, and this is a measure of the energy content of the system at constant pressure. Most reactions are carried out at constant pressure because we know what atmospheric pressure is. It's held constant for at least the duration that the experiment would be running. and we know most reaction vessels are going to be open to the atmosphere, so you'll be at constant pressure. When you're talking about this, you talk about heat at constant pressure, QP, and we just give QP a new name known as delta H, the change in enthalpy. Enthalpy is the sum of the internal energy and the pressure volume product of a system. Essentially, enthalpy is going to be a measure of the energy content of the system at constant pressure. And we're going to go about calculating delta H a couple of different ways. A few properties of enthalpy include that it's extensive, it depends on the quantities of the substances present, it's a state function, so again, it only depends on the beginning and the end, so you can do final minus initial. That makes it easy. And changes in enthalpy do have unique values. You'll see that the change in enthalpy is equal to heat at constant pressure. And we can look at these values of delta H. We have a table of delta H's of formation. Couple things I want to mention here. Delta is change in, H for enthalpy, a measure of the heat content at constant pressure, or the measure of the energy at constant pressure. This not sign indicates standard conditions, not STP, but rather 1 atmosphere of pressure, 25 degrees Celsius. The F indicates formation. You are forming 1 mole of product, and because you're forming 1 mole of product, you're going to see some funky coefficients in these types of equations. We can look at a table of delta H's of formation, and there's more than that on this table. This table's a little bit in depth. Shown here are the substances by category, so all aluminum containing substances, all barium containing substances, etc. This first column here is the change in enthalpy under standard conditions forming 1 mole of substance. So to form 1 mole of aluminum under standard conditions, the delta H of formation is 0. Here's aluminum. Here's barium, here's manganese, here's mercury in the liquid state. And what is the delta H of formation for each of those substances? 0. Any element on the periodic table in its standard state will have a delta H of formation of 0. Now be careful, because you can see mercury as a gas versus mercury as a liquid. Only in the standard state, and that would be liquid for mercury, would it be 0. Any diatomic element in its standard state has a delta H of formation of 0. Oxygen would be 0. Now be careful here. Bromine in its standard state is a liquid, so there it's 0, but as a gas, it's not. So what you want to do here is form 1 mole of substance under standard conditions. And as a result, you can't change the coefficient of the product. So you want to form, in this case, 1 mole of aluminum chloride in its standard state. The way you go about this is you start with element counterparts, aluminum and chlorine gas. And when you go to balance, you can't change that 1, and as a result, you can often find that the coefficients are going to be fractions. So what times 2 will make 3? 3 halves. So this is the one instance where you'll see that the coefficients can be fractions. Another thing I want to either let you know or remind you of, if you've seen this in the past, is be careful with the state of matter. The delta H of formation will change. Here's water, gas versus liquid, different delta H's of formation. Hydrogen peroxide, gas versus liquid. Sulfuric acid versus hydrogen sulfate in the liquid form, or in this case it could be pure sulfuric acid. Different delta H's of formation. So those are all a couple of important points that we'll get back to at the end of the lesson today.
Dr. K, why does it have to stay 1?
Because the formation value is always for 1 mole. So if you have 2 moles of it, if you had 2 moles of this or whatever, so let's say I didn't put the states of matter, but they wouldn't change. Let's say you were balancing this normally. The delta H of formation on this is negative 705.6 kilojoules per mole, 1 mole of this. Formation means you need 1. But if you have 2 moles that you're forming, what would be the delta H for this reaction? What would you guess that it would be? 2 times that is correct. And that's why it has to be for 1.
So it's whatever they give you the delta H for, that one has to stay 1?
Say it again?
So like whatever they give you the delta H for, that one has to stay 1?
Yes.
Okay.
And then in these delta H's of formation type reactions, you always have elements generating something.
Okay. So what do you do with the 3 halves? Nothing? You just leave it?
You could use the 3 halves in a stoichiometric type problem. If they gave you a certain amount of that, you would use the 3 halves the same way you would any coefficient to get, let's say, the mass of that.
Okay.
And you guys already guessed a few things here, and I think you could guess the other. These are 2 examples of delta H's of formation shown here, and again, you have to make 1 mole. Most delta H's of formation, they're synthesis reactions, so would you guess that their delta H would be exo versus endo? Which one? Exo for synthesis, and most are. If you go back and look at this table here, most of them are exo. Not all, but most are. However, in some instances, they are endo, so you would want values. So this would be an example of endo versus exo. In an exothermic reaction, delta H is negative. In an endothermic reaction, delta H is going to be positive. If you reverse the reaction, you simply change the sign. So here, this is an exothermic reaction. If I flip the equation over and the product becomes reactant, this would be decomp. This would be an endothermic reaction. Same value, you didn't change any coefficients. But as you alluded to previously, if you have more than 1 mole, you're going to multiply the delta H by that coefficient. So again, the decomp reaction we just looked at, if you decompose 2 moles of this, then you would multiply the delta H of formation by 2. In this case, it's for decomp, so you're just going to multiply this delta H by 2 to get that. So you can do a lot of stoichiometry here. And then in yellow is given, and how would you get this particular delta H? How did I get that value? What did I do? Divided by 2 and change the sign because it went from formation or at least synthesis to decomp. Pretty straightforward. And you'll see a couple problems like that in your textbook. And if you would spend the time doing it tonight, I think you'd feel a lot better about where we're going. You can draw enthalpy or illustrate enthalpy changes using the same type of profiles we did in the kinetics chapter. Let's take a few minutes to review this. Here would be energy in kilojoules, reaction pathway, the axes would be the same on both, reactant energy, product energy. The difference in energy between products and reactants is delta H. You're going to see shortly that delta H for the reaction, when calculated from delta H's of formation, is always products minus reactants. That's different from the bond energy that you were tested on in the first semester. So bond energy is always reactant minus products. But when you calculate delta H from delta H's of formation, it's always going to be product minus reactant. Be careful there. This value is going to be less than that one, giving rise to an exothermic reaction, a negative delta H. In contrast, in an endothermic reaction, what you're going to see in this instance is that the energy of the products is going to be greater than that of the reactants, giving rise to a positive delta H. So this is exothermic and this is endothermic. And you also, I'm sure, will recall that activation energy is from reactant to tippy top. And those would be reaction profiles or energy profiles illustrating the progress of the reaction from reactant to product based on changes in energy. And again, you've seen this before. Two other things I'd like to look at today, both of them very mathematical, both of them very straightforward. You can use changes in enthalpy stoichiometrically. You know that the delta H of formation is based on 1 mole, or any delta H they give you, you're really typically going to look at the products as well as its coefficient. In this example, it says calculate delta H when 12.8 grams of hydrogen gas react with excess chlorine to form hydrogen chloride gas. The equation is given, and the delta H is given as well. Is this reaction endo or exothermic? Exo, negative value. So for 2 moles of hydrogen chloride being generated, this is how much heat is released. They want to know it for this amount here. And they say in excess of chlorine, and as a result, you don't have to deal with the chlorine. That is an excess reagent, and the limiting reagent here is hydrogen gas. I'm going to convert the mass of hydrogen gas to the moles of product so that I can generate a ratio from what's given to what I want to know. So I'm going to convert the mass of hydrogen gas to the moles of hydrogen chloride, and then I know this is for 2 moles of that, and I can set up a simple proportion and show that this is how much heat is going to be released for every 12.7 moles of that substance. Give the problem highlighted in yellow a shot. Work it exactly the same way. See if you can do it. I'm sure you can. And again, this could be a non-calculator based question, but the quantities will have very simple numeric values. Make sure you do the first conversion and then a simple proportion and see if your answer matches mine. Got it, Haley? Yes, yes?
I didn't do it, but I know how to do it.
Okay. Some practice tonight would be great. All right, the last thing I want to mention, some of you have seen this previously. If not, it's really, really very easy. This most likely, well, I shouldn't say, it could be non-calculator based, but sometimes they'll replace quantities with X's and Y's to keep it really simple. If they don't, the numbers will be very user-friendly, so it won't be a calculation issue. With standard enthalpies of formation, we actually spoke about all of this already. What we're going to be doing is calculating the standard enthalpy of a reaction, delta H for a reaction, and we can calculate the delta H of a reaction right here, where you have the sum of, sigma for sum of, the delta H is the formation of the products which will be given, taking into account their stoichiometric coefficients, minus the sum of the delta H's of formation of reactants, taking into account their stoichiometric coefficients. You can calculate delta H for this reaction, showing the combustion of butane. We know combustion reactions generate CO2 and water. The delta H's of formation for each substance are provided here. Now keep in mind they might not give it to you for a diatomic element or any element from the periodic table under standard conditions, because that you know is always 0. And then it's just the sum of the product's delta H's of formation taking into account the coefficients. So 8 times the delta H of formation of CO2 plus 10 times the delta H of formation of water in the liquid state minus the sum of. So these parentheses right here are absolutely critical. You won't have the sum of if you don't include them. Be careful. Now you go to reactants, 2 moles of butane's delta H of formation plus 13 times the delta H of formation here. And you really don't need this piece here because it's going to be 0. Careful inputting into a calculator or doing it by hand. This is an exothermic reaction, which all combustion reactions are. What I would recommend that you do, either now or for homework tonight, make sure you can do this problem here. The answer is provided. Should be very straightforward to you. Actually, I take it back. I didn't give you the answer. I gave you the delta H of the reaction, and I asked you for the delta H of formation here. So I didn't give you the answer. Be very careful there. Make sure you can do it. I highly recommend many homework problems on this concept. It's an easy concept once you've practiced it. I'll work through this one and provide you with the answer either at the end today or first thing tomorrow. You've seen a lot of terms today. I highly recommend the Bozeman video on system versus surroundings. Some of you indicated that you hadn't watched the Bozeman videos until it was time to study for the semester exam. I think you regretted not watching them as we go. Really covers some concepts in great detail and provides good visuals for a higher level of understanding. Next time we'll get into calorimetry. Some of you will remember Q is equal to MC delta T, very straightforward. We'll talk about heat transfer when you've got constant temperature and work through quite a bit of this, as well as introduce Hess's law, which is very straightforward once you see it, and we'll work through that tomorrow. But I do recommend that you do that problem we left off at, and I highly recommend that you do some problems in your textbook. I think that will help you greatly. Questions?